In this module, we're going to explore Newton's laws of motion. In previous modules, we explored kinematics, which describes how things in the universe behave. Now we want to consider dynamics, or sometimes called kinetics, which explains why things in the universe behave the way they do. Underlying dynamics is the notion of forces acting on an object. We ascribe the concept of force to a variety of different things. Ultimately, the meaning of force is defined through Newton's laws of motion. Newton's first law of motion is that an object at rest remains at rest, and an object in motion tends to stay in motion, that is, constant speed in a straight line, unless it experiences a net force. So if we look at this statement, what it's saying is that a net force causes an object to accelerate. Now, these forces must add as vectors since, in the end, they result in a vector acceleration. And because forces are recognized in terms of the effect they have on the motion of an object, they may depend on the reference frame in which they are observed. This brings up a very important point. We must consider the frame in which forces are observed. An important frame is something called an inertial reference frame. This is a non-accelerating reference frame. All inertial observers agree on acceleration, and forces must be defined in terms of observations made by inertial observers. Let's recall that when we are dealing with multiple frames of reference, observers in each different frame can observe different positions and different velocities and different accelerations. But if the frames are not accelerating relative to each other, then the accelerations measured by observers in each frame will agree. And so if we have frames which are not accelerating, then these are the best frames in which we can define forces because we have eliminated all the different kinds of accelerations other than those caused by the forces themselves. As an example, consider two observers, one an inertial observer standing on the ground, and the second a non-inertial observer who is riding on a merry-go-round. And they're going to be observing somebody riding around on a bicycle. So the inertial observer observes the bike move, it will accelerate, it will sit still. There are times when it will be sitting still, times when it will be traveling with a constant acceleration or constant velocity. On the other hand, the non-inertial observer, even when the bicycle is sitting still, sees from her frame of reference, her non-inertial frame of reference, that the bicycle is constantly accelerating because she is also accelerating because she's moving in a circle. She is experiencing a constant magnitude of a centripetal acceleration towards the center of the merry-go-round. Because she observes from a non-inertial reference frame, even something experiencing no forces seems to have accelerations. So this is not a good way to observe objects in order to define forces. Newton's second law is that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. This is embodied in the equation that the sum of all the forces is equal to mass times acceleration. Now, many people think that Newton's first law and Newton's second law are really saying the same thing because Newton's second law is saying that accelerations must be caused by forces. But really, Newton's second law is saying one more additional thing that's very important, and that's about the mass. It's really giving us a definition of what we mean by inertial mass. And this is the property of an object which causes it to resist changes in velocity when a force is applied to it. It's defined so that large masses result in a large resistance to the change in velocity. That is, large masses yield smaller accelerations. So given the same net force acting on two masses, m1 and m2, the magnitudes of the accelerations they experience will be inversely proportional in the sense that the ratio of m1 over m2 will be equal to the ratio of the second acceleration divided by the first acceleration. Now, if we look at this equation, this gives us a way of defining the dimensions, the units for force. They must have the same units as mass times acceleration, that is kilograms times meters per second squared. But we use this so often that we define a new unit of measure for this called the Newton, and we designate it with the letter N, and this is the unit of force in the SI system. Now, this is a good place to remind everybody that there is a difference between weight and mass. These are not the same thing. Weight is the magnitude of the gravitational force acting on an object. So weight is mass times the acceleration of gravity. Now here we've written it in terms of the gravitational acceleration on the surface of the Earth, but in general, the weight or the gravitational force acting on an object is the mass times the acceleration experienced by that object wherever it happens to be due to gravity. All right, so on a different planet or on the moon, which has a different gravitational force acting, you will weigh something different, but your mass will be the same thing. The mass is something intrinsic to an object, whereas the weight depends on where you are and how you're moving, actually. So weight in SI units is measured in newtons, same as force, mass in kilograms, and acceleration, of course, in meters per second squared. And if we go to the imperial system of units, where weight is given in pounds, then mass is actually measured in something called the slug, and of course acceleration we might measure in feet per second squared. Now this brings us to Newton's third law of motion. This says that if two bodies interact, the force exerted on body 1 by body 2 is equal in magnitude and opposite in direction to the force exerted on body 2 by body 1. Now, the two forces which are equal and opposite by Newton's third law are often called an action-reaction pair. And given Newton's third law, students initially might think that, well, doesn't this mean that nothing can move at all? If for every force there's an equal and opposite force, then every force will always get canceled out. There will never be anything but a zero net force, so how can anything move? Well, the answer is that only one of the forces in an action-reaction pair acts on a given object. So if the action force acts on a book laying on a desk, the reaction force is acting on the desk, not the book. So, for example, an object sitting on a table experiences the force of gravity acting on it. If it remains at rest, it's because there is a second force, something called the normal force, of equal magnitude but opposite direction acting on the object, yielding a vanishing net force on the object. It is equal and opposite, similar to Newton's third law, but we know it's equal and opposite because the object is not accelerating. And Newton's second law tells us that when something is not accelerating, the sum of all the forces vanish. So this is something which can confuse students at first. You just have to remember that for action-reaction pairs, it's the force of one object on another object, which is equal and opposite to the force of the other object on the first. Okay, whereas when something is sitting around not moving, it's because one force is counterbalanced by a completely separate force that has nothing to do with the action-reaction pair. Now, this normal force, which comes into play when, for example, you set an object on a table, is a very important thing for us to consider. So let's look at this a little more carefully. Whenever you have an object experiencing a force directing it into some other object, some impenetrable, rigid object like a table, the impenetrable object, like the table, produces something called a normal force, which is directed perpendicular to its surface and acting on the object to yield a net force of 0 on the object in the direction perpendicular to the surface. All right, so this normal force is something which a rigid object can supply so that when you set an object on a table, for example, in the presence of gravity, and the object doesn't move, well, there has to be something acting against gravity to keep it from moving, and it's the normal force. Okay, this force acts all the time. For example, when you're standing up on the ground, your feet are feeling the normal force of the ground pushing up on your feet. When you're sitting in a chair, you feel the normal force of the chair acting up on your rear end, holding you in place against gravity. Now, this normal force can be whatever magnitude is needed so that the normal force can keep the object from passing through it. But of course, there's limits to this. A table can't support any possible weight. You could set an elephant on a table and the table is likely to break. So the normal force can support any amount of force needed, any magnitude of force needed to keep an object from passing through it, up to some limit where the object itself will break or deform.